Make LLMs call Python tools reliably and safely. By the end, you will have a small pipeline that turns text into tool calls. You will see how to match a user sentence to the right tool, validate the arguments, and run that tool from Python. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. LLM tools and function calling tighten the gap between a language model and real code. The core payoff is correctness. You get more repeatable answers because the model delegates facts and actions to real functions. The trade-off is latency and selection cost. Matching many tools can add time and memory. In practical terms, this pattern scales from a handful of utilities to a few hundred tools with modest engineering. The intuition is simple. Treat the model as a natural language router. It suggests an action. Your code verifies that action, chooses which tool fits, and runs it. This shines when you need precise outputs or to avoid hallucination. It struggles when prompts are vague or when tools overlap heavily. We will build a tiny demo. You will see text become a function call and then a real Python result on screen. Now we add a tiny bridge between text and functions. This snippet builds a tiny tool registry and calls a function from text. It shows how to register a handful of small utilities with descriptive metadata, so the system can map words in the user request to available functions. The snippet also demonstrates function calling by creating a natural language request, parsing what the user wants, and invoking the matching registry entry. The purpose is clarity. You learn how to structure tool descriptions so a later ranking step can compare keywords. If you change the amount of metadata per tool, you trade off speed for matching accuracy. More keywords help accuracy, but add processing time. Next, we let the model describe the call in a machine-friendly way. This snippet dispatches a function call encoded as a JSON message. It converts the model output into a structured instruction containing the tool name and argument map. The JSON acts as a contract between language text and executable code. The snippet shows how to validate JSON fields and how to respond to malformed instructions. It also demonstrates a safety check where the call is inspected before execution. If you make the JSON schema stricter, you reduce unsafe interpretations, but may require the model to be more precise. If you loosen the schema, you get more flexibility at the cost of potential errors. Next, we score which tool best matches the sentence. This snippet ranks tools by keyword overlap to choose what to call. It computes a simple match score between the words in the user message and the keywords or description attached to each tool. Keyword overlap is defined here as the count of shared informative words after light cleaning. The ranking yields a sorted list where higher scores signal better fits. This approach is cheap and interpretable. If you replace keyword overlap with embeddings or semantic similarity, you can catch synonyms, but add model calls and latency. Increasing the number of keywords per tool tends to increase true matches, but can raise false positives when tools share language. Next, we reduce noise and pick the top candidates. This snippet filters ranked tools using a minimum match threshold and top K. It applies a cutoff so weak hits are discarded and then keeps only the highest scoring entries up to a given K. The two parameters you see are the minimum match threshold and the top K candidate limit. Raising the threshold makes selection stricter and reduces false positives at the risk of missing intended tools. Lowering the threshold increases recall, but requires stronger downstream validation. Increasing top K gives you more fallback options to try at the cost of more work for later disambiguation. Next, we actually run the chosen function and return the result. This snippet completes the loop by executing the selected tool with parsed arguments. It parses the JSON argument map into native Python values, performs final validation, calls the target function, and captures the output. The snippet also includes error handling to catch mismatch types and runtime exceptions. And it shows how to format the result back into a reply that explains what happened. If you tighten argument validation, you prevent bad calls, but may reject borderline requests. If you log execution times, you can measure latency and tune the selection pipeline. Recap! It's a small pipeline that maps text to registered tools. Use it when you need deterministic behavior and precise actions. One caveat is overlapping tool descriptions, which can cause ambiguity without stronger semantic matching. Next step, tune the minimum match threshold and top K to find the sweet spot between false positives and misses. Then, measure latency and accuracy over a held-out set. If practical AI engineering helps you build reliable systems, subscribe and watch the AI engineering videos.